let's see. As I was saying, all the props to her. Anything that you don't like, it's on me, so don't blame her. Okay, so we're talking obviously about numerical domains. You have a plethora of them to choose from, depending on how complex the properties that you want to prove are and how much you're willing to pay in terms of performance for proving those properties. The basic choice, mostly for teaching and proof of concepts, are domains like signs, parity, or constant propagations. They are fairly quick, and they can prove numerical properties in very simple settings. Like here, if you just read something, and if that something is greater than 10, you perform a division. Knowing just the sign of the variable x is enough to prove that there's no division by 0. But if you change the program slightly by just adding some computation on the divisor, the sign domain is not enough anymore. So you have to switch to something a bit more elaborate that can still be non-relational. Oh, sorry, I forgot. Can still be non-relational, but that now allows you to perform some computations and some reasoning over some arithmetic expressions. Two of the most common domains are the intervals and the congruences, and just by switching to intervals, you're able to detract 1 from x and gaining an abstract value that is enough to prove that there's no division by 0 there. But you can still produce very small programs that that make the intervals domain go become completely useless. In this case, there's just an iteration over an array, and we try to print every element of the array. So you know that the length of the array is positive, but you don't really know how long the array is. And you know that the element you use for the access is positive, but you don't have any relation between the two. So one smart thing that you could do is try to combine intervals with something else, and you get the pentagons domain. Or you can move to something completely different and start to track complex relations between variables, and you get to proper relational domains. So you can sort of draw a line here, and you can argue whether pentagons should be above or below that line. But that line partitions the set of numerical domains into roughly 2 words. One that is rough in terms of precision, that works with simple properties, but it's really, really fast. And one that is instead able to prove a lot more complex properties, but it requires some computational effort. And so the work that I'm presenting kind of lies in the middle, more towards the left side, but it's still something that that we strive to define as our non-relational domain, because we want to keep the fast performances, but we still want to be able to express some relational properties between variables, and we also would like to have, as an addition with respect to the non-numerical domains that are usually used, we want to be able to tell something about values that are statically unknown, so like user inputs. Starting with an example, here there's just a small solidity smart contract. The fact that it's something that runs on a blockchain is completely coincidental. You can look at whatever other programs, but this contract has a set of accounts that hold money inside them. And there's a function set that transfers a certain amount of money from the owner of from the sender of the message to someone else. And you just have a couple of preconditions. You ensure that the amount is positive and that it's actually available on the account of the sender. And if those are true, you take out the money from the sender and you pass it to the recipient of the transaction. So what we would like to show here is that obviously only one account can increase and only one account can decrease, which seems pretty straightforward. But the problem here is that all of the numerical quantities going around here are statically unknown. The amount of money in the balances keeps changing from one transaction to the next one, and the amount is really user provided. So there's no way of knowing what values these variables will take. So this is a no-go for any non-relational domain. Every amount is top, every quantity, is top. You can refine, for instance, with intervals, you can say, okay, this is not really top, this is anything above 0. But when you take that out of something that you know anything about, you still go to top. And with relational analysis, you might learn something in these specific case, depending on the choice of the domain that you have. But even if you take polyhedra, it's easy to put some nonlinear increment here if you're not talking about money, and you get a rough approximation as well, and you'll need to move to a different domain, and so on. So the idea that we had to kind of be able to provide some intuition of what this code is doing without having to pay the price for those highly costly relational analysis is that we might, instead of talking about the values of the variables, we might want to track to speak about how they evolve during the execution of the program. So for instance, regardless of the concrete values that they might take during the program, if we know that what is subtracted here is positive, we can is positive, you can for sure say that the amount of money of the sender has decreased. It doesn't matter what actual values they are, you know that this is true. And the same goes for the amount of money for the recipient. If amount is positive, then the money he has available will be increased. And even from this high-level intuition, you see that we're not really talking about the values of each variable. Now, the fact that here there's a variable and we take it as the only thing that needs to be positive is just coincidental. You don't have any expression in here. It's not tailored to a specific, for instance, linear increases or decreases. It doesn't matter as long as you can compute, in this case, the sign of the expression that is here, you will be able to say something about the left-hand side of the assignment. But the downside is that you must be able to say something about those values. In this case, it's only the sign. You might require some more information, like the fact that it's exactly one value or that it falls inside a range of values and so on. And the stability abstract domain tries to infer these kind of properties. We defined it by first defining a small lattice of per variable numerical trends. So in here, you see that this has the same shape of an extended sign domain, the one where you have the 0 or plus, 0 or negative. And in here, you have elements to say that a variable is decreasing strictly or not, it's increasing strictly or not, it stays at the same value, or it changes, but you don't know if it got bigger or smaller. And once you have this lattice, you can just lift it to program variables. All the lattice operators are just pointwise applications of the operators from the trend lattice. And what's important here is that whenever you look at an instance of the stability abstract domain, what it's saying is how the values of each variable has changed with respect to the previous instruction. We're not tracking anything globally inside the program. We just want to know how every instruction changes the values with respect to what it was before. So let's see an example. This is the same code from before. The analysis will start by saying that every variable is stable. You don't change the values by entering a function. The two prerequisites here are just no op. Whenever you traverse a condition, you don't modify anything, any value of any variable, so everything just stays stable. And then after the first decrement, you see that all of the variables are still stable, except the left-hand side of the decrement that has now become decreasing. And when you move to the next instruction, the previous left-hand side becomes stable again because it's not modified by this instruction, but now the balance of the recipient of the transaction has increased. So as you can see, these are just relations with respect to the entry state of the computation and not global with respect to the beginning of the function or the beginning of the program. But we want to say something about the whole function or the whole program. So when you're done with this analysis, when you have a stability instance for every program point, you can just chain them. You can look at sequences of instruction and combine different instances one by one. And the way in which you combine them is just by combine the trends of every single variable by just looking at this table. If you have a variable that increased and then was stable, then overall it has increased. While instead, if it increased and then it decreased, you go to top, because we're not dealing with the values, so it might have gone back to the initial value, it might have gone lower or still higher, so you don't know, you just go to top. And when you have this chained information on sequences of instruction, you can merge them over different paths after if then else's or at loop exits by just using the list upper bound. So it's very straightforward and not really costly. So if we go back to the example from before, the chain from here to here will just be no op, because everything is stable after every instruction. The first change here is after the first decrement, when you just, the only thing that changes is on this variable here that pass from stable to decreasing, so overall it decreased with respect to the previous value. And then when you chain another instruction, as you can see this time, the first variable is still decreasing, because with respect to the beginning it went down, and you just update the second variable. Pretty straightforward. Now, I've kind of overlooked how we decide that something is increasing or decreasing. Specifically, I briefly spoke in the first example that you might need, you do need information on the amount that you're detracting from a variable, but you also need some information whenever you reset the value of a variable to a different value. Because if you perform this assignment, the variable increases or decreases depending on its previous value. So you do need some information on that as well. And we thought of this need, let's say, as our analysis needing an oracle, so something that it can query. And it turns out that there's a kind of product that exactly falls into this category, and this is the open product. So whenever you define the semantics of an instruction, you define it in terms of abstract queries to this auxiliary domain A, and you just stop at the first query that yields true. So you start, if the first query returns false, you pass to the second. If this returns false, you pass to the third, the fourth, the fifth, and the first one that returns true is the one that determines the stability of the value after the assignment. Practical note, open product is nice for the formalism, but whenever you implement this, you can just use a pre-analysis. So even if if this auxiliary domain is very expensive, you're not required to run it in combination with stability. You can just run it as a pre-analysis without incurring in extra costs, and then you can just query whatever you computed before. A couple of examples of how we define the semantics. Here you have an assignment to x that increases its value by 3 times y. And let's say that we use the sign domain as auxiliary domain in our open product. And if you try to compute the result of this new assignment by just using the sign information, you have something negative plus something that is 0 or positive, and the result will be top. So you're not actually able to say anything about the result of this assignment. But if you look at stability, and you can have any value here, I just put something random. The first thing that you do is you reset anything to stable, because every variable that is not explicitly assigned here will go back to stable. And then you begin your series of queries to the sign domain. So you start by asking if the expression you're adding is positive, you can say it. If it's negative, if it's exactly equal to 0. And the first query that returns true is if this expression is greater or equal than 0. And that corresponds to the non-strictly increase. So you're able to determine the stability of variable x in this way. As I was saying, the query go on after that in our definition. So we organize the queries in a less and less restrictive way so that the first 3 queries aim at determining strict increases or decreases. And if you're not able to say anything strictly, you move to this other queries that also apply equality with 0 so that you can have non-strictly variations. And if all of them return false, you just go to top. Let's see another example. This time we use a multiplication, which is a bit harder to handle. This time the query to the sign domain are a bit different, and specifically we query both something about the variable that we are updating and also to the expression, but this time the expression is compared with 1 and not 0. So 1 is a problematic element for the sign domain because it lies in the middle of the plus abstract element, so you're not able to tell whether an element is exactly 1. So what happens is that all of the queries that we have return false. And so we end up going to top, losing all of the information. So what you do in this case, you just swap out the sign domain with a more expressive domain. And interval here is enough to recover all of the precision for the stability abstract domain. And specifically, you're able, I just handpicked this value to make the example work, but you're able to say that x is always negative before the assignment and that the value of y plus 2 is always greater than 1. So you are able to say that the value of x will strictly decrease. And one thing to notice here is that, well, I also forgot it, sorry, from the previous example. So let me go back a bit. One thing to notice here is that when the auxiliary domain goes to top, you can sometimes recover some information. So you get something more out of your original analysis by using stability. And the second takeaway from these examples, let me find it, okay, is if you do the computations with intervals, you have an overlap between this element and this one. So you're not really sure what happened to x. But if you pair this information with stability that tells you that the value decreased, you can kind of cut off possible combinations of x before and after the assignment to refine your knowledge about what happened to x. So this was kind of the end of the master thesis from Sofia. We had an implementation inside the Lisa static analyzer working on the imp language that Lisa uses for testing, so nothing practical and nothing that we can extensively test. And the next step, so what you will see now is just a bunch of future works, is to understand where we want to apply it and where there's space to apply this domain. The first area, as I was saying from the smart counterfeit before, is to kind of try to prove some functional requirements of the program, like the fact that one account decreases and one account increases. And while doing this, you can also obtain some relational information between variables, and specifically which variables are covariant, so they increase or decrease together, and which ones are contra-variant. So when one increases, the other one decreases. This is really just a byproduct of chaining the stability information. So when you get to the end, you already can partition the set of variables by their stability value, and you can quickly see that the two balances here are contra-variant, and so you could prove potentially the non-functional requirement. Sorry, the functional requirement. But this is a bit messy because if you want to evaluate this, you will have to run this analysis on a set of programs, and every program will have its own functional requirement, so it's something pretty hard to verify automatically. A second possible application that we basically found out while writing the paper is that you can, in some cases, in specific cases, you can use this analysis to prove termination of loops. So you would start by just running the standard stability analysis. Here I left out the state from the auxiliary domain just for clarity. You will start by saying that everything is stable, then you go inside the loop, you propagate, you see that one variable increases, the next one decreases. You go back and you perform the least upper bound between the two states, and then you go outside of the loop and there's no modification to the variables. Now, instead of chaining the stability information to the end of the function, you would chain it to the end of the loops. And if you're lucky, in some circumstances, you have loop guards that are contradicted, let's say, by the chained stability information that you have at the end of the loop. So in this case, you know that you go inside the loop only if x is positive, and you know that after every iteration of the loop, x will decrease. So you can somewhat, in some situations, show that a loop will end. You don't know anything about the number of steps that it will take, but you might get lucky and be able to say that it terminates. But the probably most promising, at least in the eyes of the supervisor of Sofia, application of stability was trying to understand if the error arising from floating point computation is stable or not. So if you have a variable x that contains some floating point, you can kind of track the floating point error associated to the value of x with some ghost variable. And if you look at what happens, more or less, I don't want to upset you. I know you've worked on this. This will be very profane, so please bear with me. If you look at what happens during the evolution of this ghost variable along the program execution, you'll see that there might be some operations that are applied to x that doesn't change the actual error. But then you can have something more, some new operation that make the error become bigger, and then maybe somehow you manage to reduce it, and then you go on until you reach the end of the program. And if you track the stability of this error throughout the execution of the program, and you try to chain the information, you basically go to top anytime. You know that these errors can become, even tiny variation of this error can cause increases or decreases, and when you have two of them with opposing sign, you just go to top. So the idea that we have, but we haven't tried it at all, is to, instead of exact stability, we would like to track stability up to a sliding tolerance window that is centered around rho, that in the example that I'm about to make is exactly here, and has a breadth of epsilon. So what happens with respect to the plain definition of stability is that whenever the modifications to the error stay inside the sliding window, you deem them as stable. You can go on, and then at some point when you find an update to the error that brings the value outside of your sliding window, you say that the error increased, and you adjust the sliding window to the new value. So after that, you can start again by saying that that's stable and stable, and whenever it goes out again from that window, you update the window, and you keep going with the analysis. So the intuition that we have is that you can look at places, at portions of the code that you are analyzing and say, okay, the error inside this loop or inside this if is stable up to epsilon, but you can also change the information over the whole function, and now you're no longer going to top, but you can say that the error overall increased because you had this jump and you had to adjust the window. Okay, so just to recap, we have presented and defined a new abstract domain that is that relates the values of the same variables at different program points inside the function or the program. We are able to express sometimes information about variables that the other non-relational domain are not able to infer anything on. And we do keep the nature of non-relational domains to be fast and to scale relatively well. But this is really still a work in progress, so as I was saying, we have a number of directions to go on. We're not sure if they will work. We'll try them, and then I'll let you know. But after deciding this, we really need to go down to the benchmark, because even the fact that we are combining the domain with another numerical domains might make it not that scalable, especially if the domain is something like the octagons or the polyhedra, so that we need to assess what impact this combination has with respect to the plane analysis with just the numerical domain. And as you saw in the example from the floating point error computations, the semantics of stability is not really decided yet. Depending on the application that we have, we might need to tweak the semantics a bit, so we don't really have soundness proof at the moment. So that's also a big area to work on. Thank you.
Any comments? Yeah, Katrina.
So I have one observation and one question. So regarding the termination thing, you have to be very careful, because just knowing that a variable is decreasing doesn't guarantee that a loop terminates, because it may be decreasing a little smaller every loop, and that doesn't give you termination. So you have to guarantee that it decreases by a certain amount. So like at least 1 or something, if you have integers, for instance, or I don't know, for reals, whatever. Just decreasing is not enough, so be careful with that application if you're looking into that. The question then was regarding, so you have this oracle thing that is a sort of a pre-analysis. Is it not worth it having it as a sort of a reduced product kind of thing?
The formalization is an open product because actually we didn't see, at least for what we saw right now, the need to refine stability with, to refine the auxiliary domain with the stability information. At least not in the few programs that we analyzed. So that's why we settled with the open product. And the other reason for this is that the fact that you're defining your abstract semantics using queries doesn't really bind stability to work on a specific domain or a specific set of domain that are able to support some kind of operations. You're just querying them, and so that made the definition a bit more flexible, in our opinion.
Okay, thanks.
Okay, thanks for the talk. So you have a question on nonlinear assignments and queries. So you mentioned that the property you're looking for, sometime even polyhedra may not be enough to get it because it has issues with nonlinear assignment. And then you showed us a linear assignment and how you deal with it by doing queries to other domains. How do you generate those queries? Is it handcrafted, or do you have a general way to?
No, so what we say. Let me go back with these that are a bit faster. So like, take this example. We don't really, so the queries that we have are not dependent on the expressions that came here. What we identify is that there's a variable that appears also on the right-hand side, and that is multiplied by something. And we don't care about the structure of that something. The queries that we have is we take that something, we put it inside an equality with 1, and we pass them to the other domain. So it's up to the auxiliary domain to be able to say something about that expression.
Okay. But how do you decide which query you need to do? Like here, you do it for the multiplication. So you have you have something for multiplication, and then you deal with other kind of expressions.
Yeah, so we have one for the assignment to what we call an independent assignment, so an expression where x doesn't appear here, so like the assignment to a constant or whatever. And then we have all of these kind of expressions where x is multiplied by something, is added to something, is you take out something with a subtraction, with a division, with a power, or these are the kinds of updates we support up to now, at least. Yeah.
Okay, thanks.
Oh, just to conclude, and every one of these operations have different queries. So we have made a list of what in our eyes, but again, we don't have soundness, so we're not sure those are correct, but what in our eyes are the conditions to say that a variable is increasing or decreasing with respect to either value of a variable or the expression that happens outside. So every operation has its own queries, and we just plug the expression in and send it to the other domain. There's one there.
Oh, right, yes. A moment. 3-0 to this side.
So I have a thought about an application, which is automatic inversion. So
Sorry?
automatic inversion.
Okay.
So if a function's monotone, or like, then it's 1-to-1 and it can be inverted, right? So the thought was maybe you could use an analysis like this to say when you can provide an automated inverse. And this has showed up in a couple different projects I've worked on. One is when you're trying to do a change of variables. So whenever you have something in variational inference or in computer graphics, you'll often do some sort of change of variables. And there it's useful to have an inverse to perform that. And then also when you're doing like sparse computations, it's often useful to have an inverse map for the sparsity pattern in your computation. So I don't know. The question that I have is maybe, do you think this is related, or does it make sense?
It might. I think we'll need to chat about it a bit before understanding if it is. But definitely, I'll come back you in a bit.
Okay. More questions? I had a quick thought, maybe a little bit related to that. Here you're running your analysis forwards, as far as I could see. Would it make any sense to look backwards and see if I want this to be increasing? What were the preconditions for this?
It might. Again, the biggest driver for us to make the analysis forward were this idea from Agostino Cortesi to tackle the floating point error with this sliding window. And that was a bit why we went with the forward analysis. I think if there's an application that might be tackled with a backward analysis, then maybe yes. I think it's driven by the objective of by the properties that you want to prove.
Okay. If there are no other questions, then thank you very much, Luca.